All right, cool. Consistent hashing. So, firstly, the what is and the why behind consistent hashing. Theoretically, let's think of any app. Let's say there's an app called X, and day by day, the number of people coming onto that app is increasing. Now, if the number of people coming onto that app is increasing, therefore the number of interactions on that app is increasing, and therefore the load on, let's say, servers that exist for this app X is also increasing. What that essentially means is that we need more and more server nodes to be able to handle the more and more load that is coming onto the app itself, because the number of users are actually increasing. What that entails is that instead of, let's say, having one server, we now have four different servers. And as more users come on, we have 10, we have 15, we have 20, we have 100, 1,000, as the number of people keep on increasing and increasing and increasing. And ideally, we these servers would auto scale, which essentially means as more number of users keep coming onto the application, the number of servers actually end up increasing, proportionately to the number of users who are constantly coming, without having, let's say, an engineer or someone manually provisioning, please bring up another server, so that these systems can run autonomously. Now, where does consistent hashing fit into this? So let's say I am one of the users of the X app, and whenever I come onto the app, I am essentially running interactions. So I'm liking different posts, or let's now I'm just at this point assuming that we're going with the actual Twitter X app, but let's say I'm liking different posts, or I'm posting something, I'm doing a bunch of these interactions that you can do on the app, which would essentially require hitting the server. Now, there are a million servers, let's say, for X, the app X, because of the number of users that exist. Although million is like this extremely superlative number, we can just assume that, let's say there's 10 different servers, right? Which server do I actually end up hitting? How do we figure out where my request to, let's say, like a post goes essentially to which server? And consistent hashing is one way to be able to get there. Consistent hashing is a decently optimal solution to be able to solve for this, and it's actually very commonly used not just for this specific load balancing use case, where load balancing here means routing my request to one of the n servers that exist, but also is used very commonly in databases, for databases to scale out, or and for other resources that require possibly scaling out and require routing to one of the n nodes that actually ends up existing. And that is what I will be going over today, basically. So, the first algorithm, to be able to solve for this exact problem is round robin. Now, round robin is one of the more intuitive slash simpler algorithms. And very basically, as this diagram suggests, as one request comes to R1, it reaches the load balancer, which is actually where this algorithm is basically running, is what you can think of. And each request that comes in goes to one of the different end nodes that exist. So let's say a request named with a request ID, let's say R1, comes to the load balancer, it would go to server 1. R2 would go to server 2, R3 would go to server 3. And when we, let's say, have a fourth request that comes in, that again goes to the server 1 in a typical round robin format. And this is extremely intuitive and simple, and this is actually used fairly commonly. However, there are drawbacks to using something as simple as this. The problem with round robin, so let's say one of S1, S2, S3 actually went down. And to preface the problem and to show the problem even more, we're going to assume that R1, R2, R3, R4, which are the four requests, are actually persistent connection requests. What are persistent connection requests? So let's say we're running an application like WhatsApp, which would create a WebSocket connection with one of the servers. These are persistent connections, which means that until the user doesn't leave the app, or the connection breaks, or there is something that happens on the network layer, this connection is going to remain persistent with the server that the initial connection happened. So for example, if R1, let's say, represents me and I have logged into WhatsApp, I create a persistent connection with S1, which is server 1, and that is the server that is going to be used for all requests to be for all my chats that I'm typing in, for any other actions that I'm performing on the application itself, let's say. Um, and this context is going to help us better understand the actual problem with the round robin algorithm. So, considering all of these are persistent connections, now let's say if S1 went down. If S1 goes down, this means that all the persistent connections that lived on S1, because all of these are WebSocket connections which are persistent in nature, would now start going to S2, which means that theoretically, if S1 could handle 1,000 users and S2 could handle 1,000 users, and S2 currently has 995, let's say, S1, as soon as goes down, would route all of its requests to S2 because that is the next closest node available to it, or the next closest server node available to it. And suddenly that's a problem because S2 is not built to handle that load. And there is also an extremely high amount of connection churn, which means that all the requests that lived on S1 have suddenly now routed to S2. And 1,000, let's say, is a pretty small number. Let's say this number can be 10,000, 100,000, or whatever that number is based on how many resources exist on the server's hardware itself, how much RAM, how much memory, and things of that nature. But there is an extremely high amount of connection churn here because the moment S1 goes down, everything goes to S2. The moment S3 goes down, everything from S2 goes to S3. And those specific servers are not actually built to be able to handle that high amount of load because suddenly we've just twiced the amount of load there. And that wouldn't work. And that's one of the big problems with the round robin algorithm, let's say. And then comes IP hashing. Now, IP hashing, the algorithm, is essentially where when a request goes to the load balancer, we actually hash the IP address of where the request is actually coming from, and we mod it by the number of servers that exist. What does that mean? So let's say if the request one has an ID abracadabra, let's say it's that. When you, let's say, run a hashing algorithm over it, whether it's SHA-256 or Murmur hash or whatever other hash algorithm that's out there, let's say you get a value 9 per se. Let's just assume you get 9. And let's say you actually mod it by the number of servers. When we mod is basically going to give us the remainder. So let's say 9 modulo 3, since there are 3 nodes that we currently have, 3 server nodes, that's going to give us 0, which means that we'd go to the 0th index server. And we do this for essentially all IP addresses. And I think intuitively, like, we can already spot the problem since we're doing this by IP address, which means that if there is an extremely high amount of traffic coming from one specific region, let's say, a lot of requests are going to go are going to start going to that specific server, to that one specific server, which can potentially become an issue. And the behavior here is fairly non-deterministic in the sense that we actually don't know where the requests are going to end up going. And the issue is again in this case pretty much the same, where let's say if one server went down which was handling, let's say, IP addresses, which was handling IP addresses for a certain range, even though what range here it is actually doesn't matter because we're essentially going to be hashing the IP address and modding it by the number of nodes. But let's say a server 1 goes down, again everything goes to server 2. So this is another way, but the initial problem that we had of connection churn still exists because everything from server 1 goes to suddenly server 2, and server 2 now has twice the load it had a second ago, and it's not built to be able to handle that, and things stop working out. And we need possibly a better solution which can account for this connection churn essentially. So the intuition to the solution. So if we think about it from first principles, firstly we need to avoid connection churn, which means that in our previous solution, all requests that were routed to S1 that were, let's say, persistent connections to S1, because we're assuming a chat application type architecture here, or anything that requires a WebSocket connection, really it doesn't even need to be chat, it could even be Google Docs theoretically, because Google Docs involves running WebSockets. even though Google actually does not use WebSockets. Google actually uses a protocol called Quick, I believe. But any persistent connection, essentially. And and let's say we send the requests to S1 and S1 goes down, everything from S1 goes to S2, there's too much connection churn, all requests from S1 are suddenly going to S2. Doesn't work. We ideally don't want anything like that. And therefore, we need something that can avoid this connection churn. And ideally, if let's say S1 goes down, the requests of S1 ideally get routed to the different servers that exist. So let's say maybe get routed and load balanced between S2 and S3 so that all requests don't actually end up going to S1 essentially. And that is actually where consistent hashing comes into the picture. Okay, so what is consistent hashing? Now, to come to how consistent hashing solves this problem, I'll first talk about how we lead up to consistent hashing and what are some of the fundamental principles around what consistent hashing actually does. Sorry. So, consistent hashing requires you to create a ring, and that ring is essentially where all of your servers live. Now, this ring isn't an actual physical ring, this is more so a virtual representation of how these servers exist, but it involves creating a ring. And this ring essentially has, let's say, an S1, an S2, an S3, and an S4. And these are representation of 4 servers. And each request that comes in gets placed on somewhere in this ring. How that happens is also what I'll come into when we go into the implementation in code. But essentially, each request goes to some point in this ring. And whichever point in this ring it goes to, it actually uses the next server that is present in front of it. So let's say request 1 that exists here, it would actually end up using server 1 since the next closest server is actually S1, and the same for request 2. Request 5 and request 6 would end up using S2. So the next step in this process is essentially talking about what this ring is and what are these extra pieces that are here right now on the screen. These extra pieces are basically different virtual servers. What do virtual servers mean? So let's say we have this ring, and on this ring we have the 4 physical servers that we talked about, which are present on different parts of this ring. We, let's say, just create clones in our own head, just from a conceptual perspective, to place different servers, multiple copies of different servers at different points within the ring. So for example, if we have this big S1 here, we also place an S1 here and an S1 here at different parts within the ring, but they're essentially representing the same S1 physical server. So what that means is that let's say a request lands at let's say here. This request is technically going to S1, but actually what it's being responded to by is actually this physical server S1. So this is more so a conceptual construct of placing multiple copies of different servers within the circle, but it's essentially going back to the same server. And we will see why this is important and why this actually plays into reducing connection churn. But what we're doing is we have this big circle, and we have these 4 big servers, and each of these servers have their multiple virtual copies present at different points within this circle. Now, just from theory, let's say a request comes in, let's say at this point. If a request comes in at this point, it obviously goes to S2. Let's say a request comes in from this point, it also goes to S2, which means requests coming in here and requests coming in here are all going to S2. So let's say this totals up to 1,000 requests, theoretically. Let's say there are 500 requests here and there are 500 requests here, which are getting addressed by S2. And let's say S2 suddenly dies off. S2 goes off due to network failure or some issue like that. Now, suddenly, if you see, the next addressed server, the next server that can actually take in these requests is actually S1. But the next server here is actually S4, which means that now we had 500 requests over here, which now go to S1, and 500 requests here, which go to S4. And suddenly, the connection churn is reduced by half. And let's say this number was not 1,000, this number was 10,000, 100,000, or whatever that big number is based on the number of servers that how heavy how much load these singular servers can actually take. But this is great now because we've suddenly reduced the connection churn from being 100% down to half. And this number can obviously be variable. It's obviously not going to be 50% exactly, and there can actually be skews. Like, I think it's fairly obvious from what it is here that there can actually be skews, because let's say if there are exponentially more requests that land in this space than in this space, then, well, technically a lot of data goes to S1, but that's a limitation of consistent hashing. But the initial problem where if a server node goes down, we're guaranteeing 100% of the load going to the next node, that doesn't exist anymore. We've reduced the connection churn by 50%. And 50% is here is an arbitrary number. It can go up and down. It can also be better because theoretically, if based on the number of requests that are falling at different points, essentially. And that is the idea behind consistent hashing. And now what I want to talk through is what this circle actually represents, because this is more so a theoretical representation. And what does it actually mean? So this circle actually refers to a hash space. Now, we can think of any algorithm, hashing algorithm, SHA-256, Murmur hash, and each of these have a hash space, which is essentially this let's say 2 raised to 256, right? For SHA-256. Essentially, you have that entire hash space, and within this hash space is where each of these servers are actually present. And each request actually goes through this hashing algorithm and actually figures out each of these requests go through the hashing algorithm, and we figure out where within the hash space is this request actually going to end up going to. And wherever in the hash space it ends up going to, the next server that is present within the hash space is actually what ends up getting used to address that specific request, whether it's persistent or non-persistent, whatever it is. And also, the one thing to note here is that even if we had persistent connections, connection churn is a solved problem now. Sort of. Again, there can be skews, but it is a semi-solved problem now. Let's just put it that way. So let's essentially walk through this, right? So, like I said, these servers can be placed anywhere within the hash space. And so let's say we have a map. Let's say I want to sleep is actually the server ID of like, let's say it's the server ID of a server. Now, what essentially happens is that we loop through all servers that exist to figure out where to actually put these in the hash space. We actually hash the server ID to figure out where within that entire big hash space does this actually end up getting put. And we essentially have a simple map which is storing the server ID to where it is present in the hash space. Let's say it gave out 72. This is just an arbitrary value to represent where it is actually present in the hash space, and that is where it's going to be in the hash space, essentially. And now, why we use multiple algorithms here, I will come to that in a second. But the point essentially is that you go through all servers, let's say S1, S2, S3, S4, you have the server IDs, and you hash the server IDs to essentially figure out where they are actually going to be within the entire hash space. And now, let's say we have a request that actually comes in. Now, again, we actually just hash again the request ID itself, and we essentially go through we go through the map, which is essentially the number of the n servers that exist. And for most applications, this n server is not going to be a million. So it's actually all right to even run a simple arbitrary linear search over this. And at any point where the value of the server ID of, sorry, the value of, let's say, where it is present in the hash space, the server itself is greater than the hashed value of the request ID, we actually just use that specific server, and that's the server we're going to use. And the funny thing is, this whole ring architecture of, let's say, a request landed here, a request landed here, a request landed here, has now suddenly just boiled down to a simple for loop linear statement, linear search problem, where we hash the request ID, and eventually we just find out which is the value that exists in this map, which is actually greater than the hashed value that we got from the request ID. And also coming to why we use different algorithms. So if we saw here, we actually have different virtual servers, right? The reason consistent hashing works is because there are virtual servers. And one of the properties of hashing algorithms is that every time you would put in the same input, you would get the same output, which means that, let's say I want to sleep represents my S1 here. Every time I would pass it through, let's say Murmur hash is my hashing algorithm, I'm going to get the same place in the hash space. So the question is, how do I create these virtual servers, if that makes sense? And you do that by using multiple hashing algorithms, because different hashing algorithms would actually give you different outputs. So I want to sleep when running through Murmur hash, MD5, and SHA-256 is going to give you different places within the hash space. So this would be one place, this would be one place, this would be one place, where this entire ring represents the hash space, basically. And you do that for all servers, which essentially creates this architecture. And then eventually, it's just a simple problem of hashing the request ID and finding out which server is going to actually address that request based on iterating over the actual map we have and checking which value in the map is actually greater than the value that we got by hashing the request ID. And again, as I initially talked about it, the whole point is to reduce the connection churn. And the whole point is such that all 100% of requests should not just go from server 1 to server 2. It should be load balanced, so to speak. And this is one version of being able to load balance all requests that are coming in and to avoid that insane connection churn, with the trade-off that there can be data skews and data can actually be skewed, and we can end up with one server still being heavily loaded. But that case is significantly reduced as compared to the high p hashing or round robin, which just as soon as the server goes down, everything goes to the next available server, which is right next to it, which is what's happening here. However, with the concept of virtual servers and a hash space, it's not always going to be S2, which is next to it, let's say. So, so essentially that is that, and I will find out what next to talk about, and that should be it.